Let's start the next chapter, gas laws. This is chapter 6 in your book. Let's just dive in with a little intro here. First thing to note about gases, let's start with looking at gas pressure. Recall from physics, pressure is force divided by area. When you're talking about the gas, the pressure that a gas exerts is from the individual gas molecules smacking into each other and then smacking into the walls of the container. And so the more dense your gas is, higher density gases are going to have higher pressure. Lower density gas is lower pressure, simply because the more dense the gas is, the more molecules you have in that volume, the more collisions you have with the container, the more the pressure is. So we're going to look at these gas laws and pressure, and we're going to see it's pretty much related to the number of molecules in that given volume, and we'll show that it's also correlated with the speed of the molecules too. The faster the molecule's moving, the higher the energy that it smacks the side of the container. All right, so first thing we must look at are the units of gases, and that's part of the problem because gases were one of the first ways early chemists were able to separate other compounds from each other very cleanly with different gases. And so various people had various solutions to how to measure pressure. And we're going to start with one of the more useful measurements of pressure, the mmHg, the millimeters of mercury. This comes from the barometer invented by Torricelli in the 1600s. And it's literally just a pan, a little glass container of mercury with a long tube, skinny tube of mercury inverted in that pan. And you just measure the height of the level of mercury in the pan. There's a nice diagram in your book, level of mercury in the pan from the height of the mercury in the tube, measure it in millimeters. So that's how we came up with this really weird units of millimeters of mercury, or Torricelli was literally measuring the distance between the mercury in the pan and the top of the mercury in his tube. It's millimeters of mercury. All right, and so people say, well, that's tough to say, 1 millimeter of mercury, and so let's call it 1 torr. 1 millimeter of mercury is the same as 1 torr after Torricelli, because it's like, if you have millimeters of mercury, it's tough to say, and you say, okay, let's call it 1 Torricelli. Well, Torricelli's kind of tough to say too, so let's just shorten it to torr. Yay, everyone's happy, and we do not capitalize the T. Okay, but then people said, okay, that's wonderful for measuring the pressure of gases in containers, but aren't we currently in a gas container? It's called our atmosphere. What is the normal pressure of our atmosphere? And so what we've decided on when we look at the normal pressure of our atmosphere, what you and I are experiencing right now is pretty close to 760 millimeters of mercury. And since we normally work with our atmosphere, we said, okay, let's call 760 millimeters of mercury 1 atmosphere of pressure. So now we have a new pressure unit. We've got millimeters of mercury, which are the same as torr, and now we've got atmospheres where 760 millimeters of mercury equals 1 atmosphere of pressure, because we all like adding or multiplying and dividing by 1. And then other people got in the game. Okay, good old Pascal. And so 1 atmosphere is 101,325 pascals. If you are interested in weather, or you watch weather forecasters and stuff, when they're talking about the barometer, the barometer measures blah, blah, blah. They measure in inches because this is American. We don't want to deal with millimeters. So it turns out 760 millimeters is the same as 29.29 inches. So 760 millimeters of mercury is 29.29 inches of mercury, 1 atmosphere. Just for your knowledge, if you're watching the weather, if the temperature, if the pressure is rising, if the pressure is above 29.9 inches of mercury, that means higher pressure is coming towards us. And when higher pressure is coming towards us, that usually means better weather is coming towards us. If they say that the pressure, the barometer reads something inches and is falling, that means lower atmospheric pressure is coming towards us. That's the big L on the weather maps. And lower atmospheric pressure usually means storms, cloudy weathers, and rain is coming with low pressure. So that's why a barometer can help determine what weather you're going to see by measuring whether the pressure is getting higher or lower, the atmospheric pressure. All right, and something you might have learned in school, 1 atmosphere is also roughly 14.7 psi, pounds per square inch. We are not going to use PSI in this class. We're not going to use inches of mercury in this class. Frankly, I'm not a big fan of pascals, so we're not going to use pascals in this class. We're going to go with atmospheres and millimeters of mercury, or torr, because that's the equipment we uses those most often. All right, so because gases were fairly easy to come by, you didn't need a whole lot of extra equipment to deal with gases, we had some early gas laws. These were in like the 1660s. We came up with laws dealing with gases, and they were pretty simple. We'll go through the first one a little bit, take our time with the first one, but then the others use the same type of derivation. So our simple gas laws, and for our symbols, P is pressure, V is volume, T is temperature, N is the number of moles. We'll start with Boyle's law. What Boyle found out is that volume is inversely proportional to pressure. Volume is proportional to 1 over pressure. What that means is if you have a gas in a container, if you were to somehow increase the volume of that container, without letting any more gas in or changing the temperature, the pressure will decrease. If you increase the volume of a bubble of gas, the pressure in that bubble will go down. If you decrease the volume of the gas, the pressure goes up. Okay, well, if volume is proportional to 1 over pressure, then volume equals a constant times 1 over pressure. Solve for K and you get pressure times volume equals a constant, which means if you have a certain gas at a certain pressure and certain volume, call those P1 and V1, if you were to change the volume to a new volume, V2, you can easily calculate the new pressure because P1 V1 equals P2 times V2. And as an example problem down here, very straightforward, if you have a gas at 25 milliliter container, or in a 25 milliliter container at 2 atmospheres pressure, you increase the volume to 50 milliliters. What is the new pressure? Well, note, we've increased the volume, so we'd expect that the pressure would go down. But you just plugged in. Here's P1, 2 atmospheres of pressure. V1, our initial volume, is 25 milliliters. P2, that's what we're after. V2 is our new 50 milliliters. Math tells us the new pressure is now 1 atmosphere. Yeah, we were at 2 atmospheres at 25 milliliters, which means we're at 1 atmosphere at 50 milliliters. You doubled the volume, the pressure is now half of what it was. And the gas laws, the simple gas laws are called the simple gas laws because frankly, folks, it's that simple. All right. And so then Charles got involved here, and we came up with Charles' law. What Charles found was that volume is proportional to temperature. Okay, which means if you increase the temperature of a gas, the volume will increase. Cool. And doing the same derivations we did with Boyle's law, that means volume is equal to a constant times temperature, so then volume divided by temperature is constant. V1 over T1 equals V2 over T2. But this brings us to an important point, is that what temperature scale must we use? Volume, you could actually measure it in liters, milliliters at this point, doesn't matter. But we can't just use any old temperature scale, because what happens if it is 0 degrees outside? What happens if it's 0 degrees Celsius outside? If temperature is 0, what is anything divided by 0? That's undefined. So are you telling me if it's freezing outside, if it's 0 degrees Celsius outside, the atmosphere is undefined? No. You have to have a temperature scale where you can't really get to 0. And what temperature scale is that? Yeah, that's right. It's the Kelvin temperature scale. As we go through the gas laws, what we're going to find out is what units you use for volume don't matter too much as long as you're consistent. Your pressures don't matter too much as long as you're consistent when you're using the simple gas laws. But temperature always has to be in Kelvin. There's just no getting around it. Temperature has to be in Kelvin. And so note, it's also important because note, if you're using Celsius scale and you raise the temperature from 1 degree Celsius to 2 degrees Celsius, did you double the temperature? You went from 1 to 2, is that doubling the temperature? Absolutely not. You have to put in the Kelvin scale. That's going from 274 to 275. That's just a small increase in temperature. All right. But what happened was, using gases and using Charles' law, that's how Lord Kelvin came up with his idea of absolute zero. So what happened there? Get your book. Is Kelvin noted that you take gas, here's a gas, 1 mole of gas at 1 atmosphere of pressure, and this is temperature, this is volume. So he had started with pressure 1 atmosphere, 1 mole, and he started decreasing the temperature, and he noted the volume decreased it if he kept the pressure at 1 atmosphere until it turned into a liquid because it got too cold. But then he took another gas and did the same thing, and he got this line. And as you took these gases and different number of moles of gases, he found that, yeah, they eventually froze or eventually turned to liquid, but if you extrapolate down, all these points extrapolate down to this point right here. Meaning, as the temperature got lower and lower and lower, volume got lower and lower. But at this point, at minus 273.15 degrees Celsius, all gases have a volume of 0. All these lines extrapolate down to 0 at this temperature. And so what Kelvin theorized is you cannot get below minus 273.15 degrees Celsius because that would mean your volume of your gas would have to go negative. These lines would go to a negative volume. How can you have a negative volume? You can't. That's meaningless, so you can't get below minus 273. Turns out Kelvin was right. That's the lowest we can go. Absolute zero is the lowest we can go because gases cannot occupy less volume than 0. Towards the end of the chapter, we're going to relate the volume of a gas to the motion of the molecules. And what that's going to show us is that molecules, everything stop moving at absolute 0, and you can't have less than 0 movement. All right. Cool. Well, let's continue on with our simple gas laws. And, oh, here's a name we haven't heard in a while. Good old Avogadro. Avogadro's law. And you're saying, hey, Avogadro, isn't that the mole guy? Yep, that's who we're talking about here. And what this is all about, and this is like the most, well, yeah, that makes sense. Volume of a gas is proportional to the number of moles of that gas. The more moles of gas you have, the more molecules you have, the larger the volume of that gas, which gets us to V1 over N1 equals V2 over N2. Increase the moles of gas, you increase the volume if you keep temperature and pressure constant. And although we call it the combined gas law, the truth of the matter is Avogadro's law is not in there. But instead of memorizing Charles' law and Boyle's law, just remember the combined gas law. P1 V1 over T1 equals P2 V2 over T2. And then you can work any of these problems. What if I said, okay, you have a gas at a certain pressure and a certain volume, and you change the volume, what's the new pressure? Well, if I don't mention temperature, then we can assume temperature is constant, so whatever this number is, that one is, they cancel out. So it's just P1 V1 is P2 over T2. If I'm giving you pressure and temperature, or volume and temperature data, then you just ignore the pressures. Assume it's constant pressure. V1 over T1 equals V2 over T2. So just memorize this law and memorize Avogadro's law. And then someone said, well, that's fun, but why not combine Avogadro's law in there also? And so we kind of did, but we made a new gas law, and it's called the ideal gas law. And truthfully, the ideal gas law will be given to you on the exam, but memorize it. Memorize the ideal gas law. PV equals nRT. Pressure times volume equals number of moles times a constant R, the gas constant, times temperature. And let us work out some of the necessities of this gas law. Because we have this constant R, and constant R has units of, get this, liter atmosphere per mole Kelvin. The value of R, it's a constant, it is 0.0821 liter atmosphere per mole Kelvin. This will be given to you on the exam. You don't have to memorize this. But what it does, because R has a certain value and only has this value if you're using these units, we're going to find there's actually another R that has different units, a different number here and different units. It's the same gas constant, but used with energy. Anyhow, 0.0821 liter atmosphere per mole Kelvin then tells us what our units have to be. Our pressure has to be in atmospheres. We can't use millimeters of mercury, we must convert it to atmospheres because our constant's in atmospheres. Volume must be in liters, and well, that's just number of moles. T has to be in Kelvin. Well, we knew that. T is always in Kelvin, N is always number of moles. If you're using ideal gas law, just remember, pressure has to be in atmospheres, volume has to be in liters, because that's the units of our constant. Okay, and we can use this ideal gas law, we can do some calculations, and someone came up with a concept called STP, standard temperature and pressure. And they said, okay, when you're dealing with stuff, what are we going to call standard temperature? What should we call standard temperature? Well, we're going to call it 273 Kelvin. That's 0 Celsius. 0 degrees Celsius, 273 Kelvin, because we must put in the Kelvin scale, is standard temperature. Standard pressure, 1 atmosphere. So note, what is the volume of any gas? This is any gas whatsoever. If we have 1 mole of it at standard temperature and pressure. What's the volume of 1 mole of any gas at standard temperature and pressure? Well, you plug in the ideal gas law. Pressure 1 atmosphere. Volume, that's what we're after. 1 mole was given. Here is the constant. Standard temperature, 273 Kelvin. We do the math, and volume equals 22.4 liters. At standard temperature and pressure, any gas occupies 22.4 liters. If you have helium gas at standard temperature and pressure, 1 mole of helium gas will occupy 22.4 liters. 1 mole of nitrogen gas occupies 22.4 liters at standard temperature and pressure. All right. And then people said, oh, well, we know math. And we know that moles is grams divided by molar mass. So let's put grams per molar mass in for our number of moles in the ideal gas law. And that gives us PV equals grams divided by molar mass times RT. And what this meant, and that seems, oh, that's fine, but that means way back in the 1600s, if you had a gas in a container, if you could measure the pressure of that gas, the volume of the container, and the temperature, and if you could measure the mass of that gas in grams, you could calculate the molar mass of a gas. There's actually a nice experiment, I don't know if you'll ever get to do it, we don't do it here, where you can literally, that's what you do in the lab. You take the substance and you measure pressure, volume, the mass and temperature, and you can, from those values, you can figure out the molar mass of that gas, which gets you pretty far on the way of figuring out what the gas is. Note though, when you have this equation here, you can actually solve it for grams divided by volume. If I bring volume over to this side, I have to bring molar mass and RT over to the other side. Grams divided by volume then is pressure times the molar mass divided by RT. But note, grams divided by volume is grams per liter. Well, grams over volume, mass over volume is density. So the density of a gas is the pressure times the molar mass divided by RT. That's a nice little equation. And that's all we have for our intro. We will continue next time with Dalton's law of partial pressure.